Hi, in today's video we'll take a closer look at how you can scale your applications with InterSystems IRIS. Imagine we work at a water company. So we have smart meters sitting in every home that collect consumption information and send it to a central database. This data we'll be querying to bill our customers by calculating the overall water consumption for a given billable period of time, but also to do smarter things like try and check for leaks. For example, if for a given meter over an extended period of time, there's a consistently non-zero water consumption. As you can imagine, this data set keeps growing. For one thing, there's meter readings being generated every hour or so, but also we obviously want to grow our business and deploy more of those meters at more of those customers. So at some point, this data is going to outgrow our current server. So that means that we need to scale. Scaling can be accomplished in a variety of ways, and the most straightforward one is obviously to just get rid of this server and buy a bigger one. You simply deploy the data here and keep running there. This is straightforward, and your database will start using and start filling up the new resources. Unfortunately, when you've just switched over, you're only using a small part of the total capacity of that system. And by the time you're making really good use of it, it might already be time to look for an even bigger machine. So this vertical scaling is not necessarily the most economical model. An alternative way of working would be to start from your first server and then just deploy a second server next to it and distribute the data across the two servers. And when these guys start filling up, you just add another one and you rebalance the data across these servers. So this partitioning of data is called sharding, and InterSystems IRIS supports this very well. And it supports this in such a way that the user doesn't really have to know that this is actually a sharded cluster. So let's take a closer look at how that works. When a user sends a query to this database, he doesn't notice that actually this is a sharded cluster. It can connect to any of those servers and send the SQL query there. So imagine we're going to try and collect the total consumption of a given day's worth of data. So the system you'll connect to, the query optimizer there, will recognize that you're actually querying a sharded table, and it will try and decompose that workload. It will look for the portion of the query that it can send to the individual shards and do so. These are called the shard local queries. And in our example, this will be almost the same as the original query. It will just ask for the total consumption for a given day for the data stored on the shard you're connecting to. So all of these shard local queries lead to shard local results that are sent back to the initial server, which recombines those in a second pass, so a second pass of aggregations to send this data back to the user. Now, what does this mean in terms of workload? These shard local queries, they are affecting only the data on a given shard. So that workload is directly related to the amount of data on every shard, which means that if we distribute our data randomly or evenly across these servers, the workload that's nicely parallelized here is also distributed evenly. So we make a really good use of our resources. Now, the recombining part is something that can happen on only one machine. That's user-bound, which means that if we just wire through a load balancer our users to different machines, just distributing that workload, we again get an even spread, and we have a nicely linear scaling model for our horizontal scaling mechanism. So far, so good. This was a very straightforward query. Now, let's look at what this means if we have a slightly more advanced query. Say, the query that calculates the overall consumption per meter. In this case, if we distribute our data randomly, that means that data for any given meter can be distributed, can be spread across all machines, which means that it will also be spread across all of these shard local results, which means that this recombination part will be a lot heavier. This is where the distribution of your data comes in. That's what we call the shard key. The shard key is a choice you can make when you define your table that identifies a particular column that InterSystems IRIS will use to decide which record goes where. By default, it's automated and it's completely random, which is fine for many cases. But if you know what kind of queries you'll be getting, And if there's a particular column that's often used as an aggregation key or a join key, it becomes interesting to choose that as the part of your shard key. Because the effect of that is that all the data associated with any given meter ID, in the case of this sharded table, will be stored on a single shard, which also means that it will be guaranteed to be part of only one of the shard local query results, which means that the recombining of these query results becomes a simple union rather than doing a totally new aggregation. So that's making sure that we're pushing down the work down to the shards, which can execute it nicely isolated in a totally parallelized way. This is also extremely interesting if you have common join patterns. For example, if you have your meter and your readings table, and you want to make sure that the records for 1 meter and the corresponding reading are all stored on the same table. So by making sure that those tables are co-sharded, by giving them the same shard key, you can make sure that the join operation can happen totally locally in every shard, thereby making the most efficient use of your resources. That was how InterSystems IRIS supports sharding in a nutshell. There's many other interesting capabilities in InterSystems IRIS that allow you to scale flexibly. More about that in the next video.